Well, it's subtitle for part of this lecture, so I'm going to talk. So today I'm planning to talk about random walks with an arbitrary starting point first. So let me remind you what I did last time. Last time we considered a random walk with zero mean and finite variance, started at zero. Okay, and then we will define the first ladder epoch, tau was defined, and what we did eventually, so we proved that under the assumption that expectation of x is 0, variance of x is 1, the asymptotics for the exit time is square root of 2 over pi 1 divided by expectation of modulus as tau, so that's the expectation of the first ladder height times 1 over square root of n as n goes to plus infinity. So that was the last theorem I managed to prove. Now what I'm going to do today, first I will now consider a random walk which starts at point x. Okay, so then, well, we have a choice of notation. I will use this one. So basically my new random walk is just x plus Sn, where Sn my old random walk. So that's my process, and greater than 0. So S0 is equal to 0. We have an initial position here, and then this random walk starts to oscillate, and eventually we can define the same stopping time. So the first time this random walk will start at x, exits the positive half line. Now this will depend, of course, on this initial position. So now x is the first time and greater or equal than 1 when x plus Sn is strictly less than 0. Okay, so now I'm going to work with this stopping time. For my next aim, next objective, is to find asymptotics for our probability tau x greater than n and goes to plus infinity. Okay, so that's what I'm going to do next. Well, again, there are several approaches to this problem. So one of the approaches would be to use the Wiener-Hopf factorization, and then you can work this out. So I'm going to use a slightly different approach. So I will try to use these asymptotics, so the one which we already know, and plus some extra arguments which will allow me to obtain this asymptotic. Okay? And the arguments which I'm going to use are based on the ladder heights and ladder epoch. So how can we split this? How can we represent this stopping time tau x? So our random walk starts at x. Okay, so let's wait until this random walk will go below level x for the first time. Okay. So that's going to be my random variable tau 1. I'm basically because random walk is space homogeneous, so what we are waiting for, so we can forget about x, we're just waiting for the first time when Sn becomes less than 0. So that will be exactly tau 1. So tau 1 is equal to tau, right? So that's just.
There is confusion in notation. I use tau x, man.
Tau 1 looks like you're starting to walk from 1.
Right, so that's the thing.
Put brackets around x.
Tilde, give it a tilde.
Brackets around x.
Just put the tau dash. Why should it be tau 1?
Give it a
Give it a
hat.
hash.
Because it's going to have a tau 2 as well.
So if I put it here,
Yeah.
will you feel better?
Or just in brackets. Like
Oh,
tau
brackets
hash.
probably better.
Yeah.
So let's put brackets around x. Okay, so tau 1 is equal to tau. Now another thing is that this is our letter height, chi 1. Right? So now as the first time we went below level x, went below level x by this amount. Now we can start our random walk once again. So we start from here, and then we run again random walk until it becomes smaller than this level. So this time, this is tau 2. Tau 2. Now by the strong market property and by the fact that we have ID increments, tau 2 has the same distribution as tau, and tau 1 and tau 2 are independent of each other. Okay, so they're independent of each other, and again, we can recall that the amount by which we are going to overshoot is chi 2. Okay, so basically we can repeat this procedure. Okay, so that's our tau 3. So here it's going to be tau 4. Well, and here what happened is that at time tau 5, our process went below 0, and that's our and that's what we are looking for. So now what we know is that so clearly tau k kappa k is a sequence of I, D random vectors. Okay, so we have random vectors. Now how can we identify tau? So on this picture, tau x responds to this direction. On this picture, tau x is simply the sum of tau 1, tau 2, tau 3, tau 4, and tau 5, right? So for this trajectory. But, yeah.
So you're looking for the first case such that the sum of the chi's is bigger than x.
Yes. So what I need an extra stopping time, and that's what Mark said. So I'm looking for the first time, so let's call it mu of x. The first time and greater or equal than 1 when chi 1 plus chi 2 plus chi n becomes greater than x. Okay, so that's how you can define. Well, from this picture, so this happened at time 5. Well, it might be some other time, but important thing is that, well, mu of x is just the stopping time with respect to the filtration generated by this sequence. Okay, so now this is mu of x, and with this mu of x, tau of x well, let's put some notes, right? So let mu of x has this representation, then tau of x is just the sum of tau 1 plus dots plus tau mu. Okay, and this is almost sufficient for our purposes, right? And basically, to derive asymptotics from this representation, I need an extra thing, which I will explain shortly. Okay, so that's a theorem. That means a theorem HT. Okay, so basically what we know asymptotics for tau, and we want to derive asymptotics for the random sums of taus, right? And there is a result which says, so let y1, y2, and so on be a sequence this and mu. Well, no, first we need some assumptions. So let's consider. So we can consider positive random variables be a sequence of positive or non-negative random variables that's sufficient, such that probability that y1 is greater than y behaves like y to the power minus alpha as y goes to infinity. And I have to assume that alpha belongs to 0, 1. So alpha belongs to 0, 1. So effectively we are looking at random variables with infinite mean. Well, you can multiply y minus alpha by solid variable function as well. So let's put C here. Some positive constant. And so let nu be a stopping time. For us, it's sufficient to have a stopping time, but well, more generally, it can be a random variable which does not depend on future. So it defines filtration and it doesn't depend on future. It's very similar to the both identities. Let nu be a stopping time. Then probability that y1 plus dots plus y nu. Well, I should have said that stopping time with respect to the filtration generated by this random variable. So probability that y1 plus y nu greater than x is the same as expectation of nu times probability that y1 greater than x as x goes to plus infinity. Okay, so that's the theorem which I want to use. I can give you a reference, just let me check. That's Greenwood and Moon.
Okay. This nu here is a stopping time with respect to which filtration?
The Y's.
Generated by Y's?
Yes, it's so here
As you
it's
said.
yes. Generated by Y's.
But it's slightly different situation.
It's slightly different, but well, that's what they proved. And well, I can assure you that the same thing will hold in this slightly different case. Okay, so let's begin with Monroe. Yeah, so basically, wait a second. So here another formulation will be much better. So if it doesn't depend
On the future.
on the future, so
Yeah.
then everything will be fine. So, okay, so let me be. So let me formulate. So let new be a random variable. Does not depend on future. That is tau when tau greater than n is independent of the sigma algebra generated by
Is tau new?
it should be new. Yes. Mu greater than n is independent of the sigma algebra generated by y n plus 1, y n plus 2, and so on. Okay, so that's the thing. So now we are okay. So if this holds
For every n.
for any okay, so that's the assumption. And then probability that y1
It's opposite. I'm thinking probably you need this one to be independent of sigma field generated by 1 to yn.
No.
No?
No. Because you know if mu has happened or not by looking at
Mm.
well,
yes, so basically
That's why it's called independent on the future, not on the past.
yes. So it might depend on the first n observation.
if you want, you can change the first event to nu less than or equal to n, and then
Mm.
you won't be
Yes,
Mm.
will be better.
All right. Right.
y1 plus y new greater than x is the expectation of new probability that y1 is greater than x. Okay, then I should not really use this reference. So if I use this statement, then I have to refer to another paper, but well, basically almost the same thing was proved in Greenwood and Monroe, 77, and the version with the random variable that does not depend on future is something that can be found in a portion of probably 2011.
So if the expected value of nu is infinite, this doesn't tell you a whole lot.
Well, if expectation of nu is infinite, well, it tells something, but it is basically useless indeed.
Yeah.
But somehow it's a more complicated case, because if it's infinite, then in general you might get a different answer. So if you plug in independent, new which is independent of the sequence, and if you do computations, then you will see that there might be some kind of different answers. So basically, so I'm not going to prove this. I will just comment. I'll make two comments. The first one is, so this is some kind of usual heavy-tailed statement, right? So in the world of heavy-tails, so what do we have usually? So this is something that might be good to do as a homework. So basically, a very common thing is that if you have two random variables with these tails, then what you can prove, and I encourage you to try to do this, is that you have this asymptotics when x goes to plus infinity when you have two random variables. Okay, so try to do that homework. That's homework. And then basically by induction, that's the second homework, you can extend it to the case of n random variables when n permits y1 greater than x, homework 2. And here, well, so here you need to do some extra work because this is no longer a deterministic number. So here I have a random variable, and in the independent case, this is something like the sum of 1 to plus infinity and probability y1 plus yn greater than x times probability nu equals n. So it is independent. Somehow this is well, you need.
Maybe you don't need n in front yet, no?
Yes, now we don't need n. So basically, if you notice, then what's happening is that this is equivalent to n probability y1 greater than x. So what's written here is this left-hand side when nu is independent. Okay. So now we're replacing this by n probability y1 greater than x, and then you can see that you're going to get probability y1 greater than x times expectation of nu. Okay, so this is not fully true because you need to justify the limit, but well, you can do it. Now so this is the first comment, and the second comment is that you can also think about this as some kind of extension of the world identity. So basically, another way to prove this formula is to notice that first expectation of y1 plus y nu. Now these random variables do not have expectations, so I need to truncate them, obviously. So if I truncate it at level x, then that's what is done in this paper. Then you can prove a sort of the world identity, which says that this is equivalent to expectation of nu times expectation of y1 minimum with x. Okay, so that's the first thing that you can do. So now everything is well defined because they're all truncated. For the world identity to work, well, you just take x equals plus infinity, but this will work only if y1 has finite mean. Now, so that's the first step, and then what you know that this behaves like some constant x1 minus alpha by Karamat theorem.
Dennis, do you want the min x to be with every one of the y's individually? In this
Well, yeah.
Yeah.
No, I want exactly this thing. So I want expectation of S nu minimum with x to behave like the right hand side.
Is this statement also true for slowly varying tails? distribution?
I don't think I believe this statement. Sorry.
You don't believe it?
Well, if nu is independent of the y's and geometric, and it's got a very small probability of being a success, so that's an enormous sum of y's, then the minimum of those two things is actually just x, basically. So you've got x on the left-hand side, and on the right-hand side you have something that grows massively.
Yes.
I don't understand.
Well, basically here x goes to infinity, so nu can be very small, but it doesn't matter because x will dominate everything.
Okay, x is going to.
Yeah.
This x.
Yeah, x goes to infinity. So basically, right. So this follows from Karamata theorem because, well, there is no harm in explaining this. Expectation y1 greater than x is just integral from 0 to x probability y1 greater than t dt. Okay, so when you plug in your expression, you're going to get an integral from 0 to x t minus alpha dt, and then you can see that this is the same as 1 minus alpha x.
So, Denis, is it minimum of y1 and x in the first line?
Sorry, yes.
And then there should also be the term corresponding when it is x, but it will be negligibly small. So it's not equality in the
It's
first.
equality. So first is equality.
But what happens when you got x? The minimum is x. Then you just have x times probability.
No. So
That's
this-
y1
No, no, no.
is.
So what you're saying is that so you're suggesting to write expectation of y1 minimum with x as integral from 0 to x.
Yes, you're right. Yeah, because you already done. Yep,
Yeah,
yep,
so you
yep,
put
yep.
t
You already done.
probability
Yeah, sorry,
y1.
sorry. It's already there. Yep, yep.
I can't stop.
You can't stop, man.
So I said, my question is for this statement here, is it also true for the tail to be a slowly varying function?
Yes, it's fully varying function.
All this, yeah, slowly
Will
varying
work.
function.
The only thing that you need alpha to be less than 1. So you need the infinite mean, then everything will work as it should be. Okay, so basically, so this is sort of both identities. Now you have the right hand side is easy to compute, and therefore this thing will behave like so there should be C as well because there was C. So this thing will behave like exponent nu times C over 1 minus alpha x to the power 1 minus alpha. And now what happens is that actually you can write this thing in the same form again, integral from 0 to x probability as nu greater than t gt. And then you can somehow find out asymptotics for this thing because it's monotone using the Karamata theorem. And then so behave like expectation nu c1 minus alpha x 1 minus alpha, and then apply Karamata's theorem. Okay, so that's, well, so if you believe that world identity is true in this form, well, one bound in one direction is actually very easy, right? So y1 plus y nu minimum with x is always less or equal than y1 minimum with x plus y2 minimum with x plus y nu minimum with x. And then what is always true is that this thing is always less or equal than expectation y1 minimum with x plus y nu minimum with x, and that's somehow the same thing as expectation of nu times y1, expectation of y1 minimum with x. So the more difficult part here is to get lower bound, but this can be used. So this can be proved using the standard one big jump approach. So that's what was done in this paper. Of course, and so on. So if you're interested in details, okay, so that's the theorem which I want to use. So now this theorem, so we need first to check conditions. The first condition is that probability tau greater than n behaving like C times 1 divided by n, and the power here is less than 1. So that's the power which I have is 1 over 2. So I can indeed apply this theorem. By theorem HT, probability that tau x greater than n is equivalent, so expectation of mu of x times probability that tau 1 greater than n as n goes to plus infinity. Okay, so that's what we have. Now we just need to somehow recognize what this expectation of mu of x is. Okay, so I can, so that we need this bit.
So just to avoid some confusion, this x is completely unrelated to that x.
So this x is fixed, while x on that whiteboard goes to plus infinity. So x there is n here. Okay, so now, well, before I give a statement, I just need to make final rewarding. So what is the expectation of mu of x? Basically, you can, or maybe somebody knows. Question mark.
So there is
So, well, you can try to recall what it is, or you can just compute. So, expectation of mu of x. So, mu of x is an integer variable. So, this is the sum from 0 to plus infinity probability that mu of x is greater than n. Okay, so that's one of the formula. Then this is the sum from 0 to plus infinity probability. Now mu of x greater than n happens if and only if the sum of chi1, chi2, chi is less or equal than x. Okay, so that's the same thing as probability chi1 plus chi less or equal than x. And now you can recognize that this is nothing else but the renewal function, which corresponds to the decreasing ladder height process. And the name of this function is v of x. Okay, so that's the notation I was using for this function. Okay, so now we have everything in place, and I can formulate my theorem. So that's theorem 2 or 3? 3.
3,
Oh,
at least.
Theorem greater than
theorem 3. So let x is greater or equal than 0. So let expectation of x is equal to 0 and variance of x is equal to 1. Then probability that tau x greater than n behaves like b of x probability tau greater than n. Well, I can write down this explicitly. That's square root of 2 over pi, 1 over expectation of I times v of x times 1 the square root of n as n goes plus infinity. Okay, so that's the statement which I wanted to prove. So in principle, I can move on to a random walks condition to stay positive, but before doing this, I need to discuss one property of the function v of x. So this function has a very nice and useful property. Okay, so which function v of x plays an important role, and it plays so I need one more fact. It's a theorem for function v of x is harmonic for the field random walk. And I will explain shortly what this means. So that is expectation of v x plus s1 indicator tau x greater than 1 is equal to v x where x greater or equal to 0. Yes, that's what we understand by being harmonic. And in particular, Vx plus Sn indicator tau x greater than n is a Martin. Okay, so that's the statement of this theorem. So in principle, it can be proved in a general way, but it requires more knowledge about the Wiener factorization. And here it can be proved if we use a representation for the function v of x, which follows from the Wolf identity. Okay, so let's so I'm not going to give this proof, but I will just tell you how you can try to do it. So you can we can use. So in our situation, we can use the following representation. b of x which follows from So if you remember, we have our random variable nu of x. Then what happens is that we start at x, and then we have this overshoot. So basically we can write it in two ways. So that's x plus s tau x, the position that we have here. So that's one way to write it, and another way to write it is that this is the same thing as chi 1 plus chi nu of x. Okay, so minus x, sorry. Minus x. Right, so that's. So if you remember our ladder height process, so that was chi 1, then there was chi 2, then this is chi nu of x, and then basically we know that this distance is x, so then this will be the sum of chi 1 till chi nu of x, so, and then this thing will be represented as the difference. So taking the whole sum and you subtract x. Does this make sense? Okay, and then you can see that x can be cancelled, and we have expectation of s tau x being equal to minus expectation of chi 1 plus chi nu of x, but this thing can be found. Just the water data that we need to apply, so that's minus expectation of chi 1 times expectation of nu x, and then this is minus expectation of chi 1 d of x. So basically, from these we obtain the formula for b of x. So b of x is equal to expectation of s tau x with minus divided by expectation of chi 1. Okay, so that's the representation for b of x, which follows from the Wahl's identity. And now, well, if you use this representation, and again, I'm going to leave this as a homework. So basically, because, so what I want to prove star. I want to prove this equation. Now, so we should really care about constants in this equation, right? So if you multiply b of x by any constant, it won't change this equality. So basically, this representation tells that hence it is sufficient to prove that so if we take expectation of s tau x and plug in instead of b of x, then we should have equality. So it is sufficient to prove that expectation s tau x plus x capital tau x greater than 1 is equal to expectation of s tau x. Okay, so
So
that's
you've got a condition, you've got some condition on the center of the left-hand side. Condition on,
so what I have, I just plugged in this quality. So that's so this corresponds to S1. So X capital is independent of all the things here. I see what you mean. Just a second. So after you've done this computation, you have to have X, right?
The condition on tau x.
Yes, it should be conditioned on
X.
should be conditioned on X.
It's suspicious.
maybe if we write down, because we're looking from board to board, if we
Yeah.
write down what it is that we're actually,
Yes, okay, so what we have, so we have expectation of V X plus S1 indicator tau X greater than 1. So we want to show that this is equal to V of X. So we don't care about constants.
Yeah.
So on the left hand side, we can plug in expectation of S tau X right away.
so I believe what you have as a statement now.
What do you mean?
I believe that is sufficient to show what you said. I think that's correct. Other people can disagree.
It is sufficient to believe it is sufficient.
Well, okay, so probably, well, just to avoid any kind of problems, so what we can actually do, we can just write down what this thing is. And that will be the first part of the proof. So what this thing is that expectation V X plus 1 on the event X plus 1 greater or equal than 0. Okay, so that's exactly the same thing. Now, therefore, this is equal to integral from minus x to plus infinity f of dy. Expectation v x plus y. That's it, right? So that's the left-hand side. And now we can just plug in the expression that we've got. This is the same as integral from minus x to plus infinity f of dy. Now you have to multiply minus 1 over the expectation of chi. And now here everything is clear, right? So these are just constant x plus y. So you have expectation as tau x plus y. Right? And this should be equal to minus 1 over expectation of kappa. Expectation of s tau x.
So silly question. On the first line, x capital, you said it's distributed like S1. It's just the first jump. How is it related to tau x? Because you got tau x there as well, right? Integrating over the event tau x greater than 1. In the very first line.
Okay, so just ignore the very first line. So because what I did, I just formally.
Okay.
So it doesn't look good, the first line. So what I did, I just formally written down, right? So Vx. So this step is just the definition, and now I plugged in my expectation of Vx plus y, which I computed on that blackboard.
It's funny because it's deterministic.
But everything is deterministic here,
Yeah.
both left and right side. So what you might want to do is just cancel those two things. Yeah, maybe I could give a proof then. Okay,
I think it's okay.
It's time to have a break now. Give it as a homework.
Okay, so you can finish the computations and prove this result. So it was a more generality, but well, somehow this way is something that you can do directly without any knowledge of the mineral factorization, right?
Break?
Break.
Break.